All right, everybody, let's get started. So this week is our first week's unit on waves. So specifically, we'll be talking about solutions to the wave equation like pulses, traveling waves, and standing waves. We'll be talking about energy carried by a wave, superposition, and how that connects to ideas like interference and standing waves, reflection off of barriers. We'll talk a bit about the Doppler effect, um, and identify what we mean by like resonant frequencies and how we figure out like what frequency a musical instrument will play. So one of the units that comes up this week is superposition, which is the idea that because I can make waves of pretty much any shape, traditionally we think about like sine waves or cosine waves, but really I can make all sorts of pulse shapes that aren't periodic. And my wave equation is a linear equation. And so that means that the sum of any two solutions to that wave equation is also a solution. So if I have two waves traveling past one another, the result is just the linear sum of the two individual waves. So I mean this quite literally. So as an example, if I have two waves approaching one another, these two waves will approach one another at the same speed, because the speed of a wave in a medium is independent of things like amplitude and wave shape. So if I want to figure out, say, the height of a string when I have a combination of multiple traveling waves, I can literally just move the wave crest a certain amount of spaces, right, and sketch each of the two participants. And the resulting wave is literally the sum of the two involved waves. So one kind of fun, maybe unexpected way we can use this is to think about what happens to a wave at a boundary. So if I, for example, have a fixed boundary, like I have a wave on a string and I've tied the string to a spot on the wall, so it's not free to move up or down. That point on the wall is what we refer to as a boundary condition. So when I'm solving the wave equation, I now get this extra condition that the height of the string always has to be 0 at that point. And one way in which to guarantee that we're solving the equation correctly is to have a pulse that's approaching the wall, and I can use superposition to figure out the actual solution of the reflected wave. So the wave I'm going to use for superposition is a wave that's identical to the incoming wave, but flipped, right? Both upside down and reversed. So if I superpose a solution, if I imagine that the string, like pretend really that the string carries on past the barrier, and imagine a wave coming in from the imaginary string, if that wave has the right shape, then it will always cancel out at the boundary. As a result, I can use that to prove that the wave coming back from the boundary is always going to be upside down. So waves or pulses traveling at a fixed boundary like this are reflected upside down. This extends to thinking about waves traveling on strings if I, say, change medium from a light medium to another medium. So in the case where I have a wave coming in on a light string and it's tied to a heavier string, that change in medium results in a wave that travels more slowly. So that's a little bit like a fixed end, and so the resulting wave comes back upside down. Meanwhile, if I were to send a wave in on a heavy string into a light string, that wave would propagate right side up, and the reflected wave would also come back right side up. So this seems like a weird thing to kind of obsess over, but this actually becomes really useful when we start thinking about other kinds of waves, specifically light. So we talk about like the speed of light being 3 × 10⁸ meters per second. That's the speed of light in a vacuum, but in other materials, light travels more slowly. So for example, light travels in water more slowly. So if we want to figure out what's going on at the interface between two different materials when light goes from one medium to another, this reasoning of thinking about like a wave on a light string versus a heavy string becomes really conceptually helpful to explain what's going on. So that's the reason why we're kind of introducing this, what seems like kind of a really niche case. So thinking about the problems that we worked on, some of these conceptual problems are just trying to get our head around, right? How do these traveling waves work? And so the idea is we can kind of think about every point on the pulse shape traveling at the same speed down the string. So in this case, if my hand takes a quarter second to make this pulse, that means if I'm standing and watching the pulse go by, it'll be a quarter second from when I see the beginning of the pulse pass me to when I see the end of the pulse pass me. And so I know that this takes me a quarter second because between making the beginning of the pulse and making the end of the pulse, the beginning of the pulse has moved a distance of 10 centimeters, and I know the wave speed on this wave is 40 centimeters per second. Okay, so then in the second question, we started thinking about connecting waves or connecting strings at two different densities. And one of the tricks here is to remember that if I tie two strings together, they necessarily have to have the same tension. And so the way we can reason that out is by looking at the point where the two strings meet and drawing a free body diagram at that point. So that point is not accelerating left or right. So I know whatever the left force and right force on that point are have to be the same. So I can conclude that the tensions in the two strings have to be the same. Therefore, when I go to figure out the velocities, I'm just comparing the mass densities. And so if the tensions are the same, the lighter string is going to have a smaller mass density. So there's something like mass per unit length. Typically the units we see for that. So the lighter string has a smaller mass density and therefore a larger velocity. Now, if I imagine I have that boundary and two waves are approaching separated by a certain amount of distance, it's really interesting to talk about what happens when they transition onto the next string. So after they've transitioned, right, they're still going to be the same time apart. And the reasoning for that is if this wave arrives at this point 1 second earlier than the second wave, and the second wave will be arriving here after, right, this has traveled a certain distance, but it's still moved like 1 second past the point where it arrived at the boundary. So the timing between those two pulses is going to be the same. If they arrive at that point 1 second apart, they're going to leave at that point 1 second apart. Now, in terms of distance, because the wave speed on the heavier string is slower, the front pulse will have traveled a smaller amount of distance in that 1 second. So same amount of time, smaller velocity, than a smaller distance. So when I think about the separation between these two pulses, they're still 1 second apart, but the distance between the two pulses is now shorter. So again, why am I kind of bringing this up? This seems like a really niche kind of discussion. Again, this is going to become really helpful when I start thinking about light and other more complicated waves. So what we're going to be able to draw from this is the idea that if I have a periodic wave approaching a boundary, the timing between two crests is going to be the same. Or in other words, the frequency of that periodic wave is going to be unaffected moving from one medium to the next. So the timing is going to be the same, the frequency is going to be the same. But because the speed is different, and I have, right, speed is going to be wavelength times frequency, the frequency is going to be the same, and the wavelength, therefore, is going to have to be smaller. So when waves change mediums, we're going to figure out the new wavelength in the new medium and keep the frequency the same. Okay, so the next set of questions, we're kind of talking about energy. And so for energy, right, we have this idea of power, and that as I get further away from a source of sound, the same power is being distributed over a larger and larger surface area. So, right, sound is quieter the further away I get from the speaker. And in terms of intensity, that goes like 1 over the distance squared, right? So the power looks like, or the power rather over the surface area, so 4 pi times the distance squared, that gives me the intensity. So when we hear sound, we hear intensity, but we hear it on a logarithmic scale. And what that means is if something sounds twice as loud, it's actually more like the amplitude of the wave is squared. So the decibel scale, this log scale that we come up with, that's really just there to reflect more accurately our experience of sound, right? Because if I double the power of the sound, it doesn't actually sound twice as loud. So the equation we have for the intensity in decibels looks really strange and really arbitrary, but it's based on the physiological functioning of the ear, essentially. So to find the intensity in decibels, I take the intensity in watts per meter squared, and I divide by this 10 to the negative 12. This 10 to the negative 12 is representative of the quietest sound that the average person could hear. So that's why it's in there as kind of like a calibration, right? The stuff that goes into the log function has to be unitless. So I calibrate my intensity to the human ear. I take the log and multiply it by 10 decibels to get it in the right set of units. So again, this is based on the idea of the way that humans hear and what sounds twice as loud to us in our kind of subjective experience. So me talking normally in a lecture hall, it would typically be around 60 decibels, and a jet engine, if you were standing 60 meters away, would be 120 decibels. But that's a log scale, so it's not accurate to say that I am half as powerful while talking as a jet engine, right? Like doubling the decibels is squaring the power. It's a lot more power. And the difference between it's like someone whispering and a jet engine is 1 billion watts per meter squared, right? So that scale is getting compressed into make this log scale that's just more reflective of how we engage with sound. Okay, so if we're thinking about periodic waves, then we are going to start asking questions about frequency and wavelength. And this is going to start tying into Doppler effect. So the first of the questions that I asked about this is not actually really a Doppler effect question, because I made sure to say that the source is stationary. So if a source is stationary, then I have no Doppler effect going on. And what I'm imagining happening is somebody has to be turning a dial on the sound to make it a higher and higher frequency. If the frequency is increasing, the wavelength of the sound waves has to be decreasing. And the reason we know it has to be decreasing is because of this idea that the velocity is not dependent on what's going on in terms of frequency or amplitude, right? Just in the way that the period of an oscillator didn't depend on the amplitude of the oscillation. The velocity only depends on the medium the wave is traveling in. So for sound, this depends only on things like pressure, temperature of the air, things like that. How it depends on those things is actually kind of a complicated function. So typically, if we have a problem to do, I'll say, hey, today, in today's conditions, the speed of sound is 340 meters per second, or something like that. There are some formulas out there, but they're empirical and they're pretty complicated. But it will vary a little bit day to day just based on barometric pressure and the temperature outside. But it's going to be in the neighborhood of 330 to 340 meters per second. So again, the question following up that one, if I'm adjusting the pitch, the velocity is not changing, right? Probing the same issue. Okay, so now we're starting to think about Doppler effect. So I do have a video, right? One of the individual assignment videos is on Doppler effect. I really recommend that one. I mean, I know you should be watching all of the pre-class videos, but definitely the one that I made about Doppler effect, because the equation for Doppler effect is a little bit complicated, right? So I care about like the velocity of the source, the velocity of the observer, the frequency that you hear, the frequency that's being made, and there's these pluses or minus signs in the equation, right? And there's a lot of plus or minus. And so you have really two options. You can memorize all the different cases and which should be plus and which should be minus. But honestly, I never remember. And I think it's much more valuable to have the intuition about what do I expect to happen with the frequency. And so this intuition comes from if you listen to, say, like a siren coming by or a car engine going by, as it's approaching you, the sound has a higher frequency. And as it's moving away, the sound has a lower frequency. So that's the intuition that we're asking about here. As this source moves away, or you move away from the source, the frequency is going to be smaller than if you were both stationary. So the tone will be lower. This intuition is really valuable, like I said, because we probably need to check when we use the Doppler effect equation to make sure we've used the right signs, like positive or negative signs. And for me, falling back on this intuition is always the best way to do it. So now I've asked a slightly different question where I'm talking about the wavelength. So again, that video I made about Doppler effect on the learning glass is super, super important here. And I derive the equation, I talk about what's going on with the frequency and the wavelength. But the thing to remember about that is that the wavelength only depends on motion of the source. So in my analogy, right, in the pie making conveyor belt analogy that I use for the Doppler effect, only the person who's setting down the pies is involved in determining the physical spacing of the pies on the conveyor belt, right? Only the thing making the sound is determining the separation between crests. If I am the receiver of the sound, moving towards or away from the source will affect the timing of the crest. So it'll affect the frequency that I receive does not affect the physical spacing thereof. So it doesn't affect the actual distance between two of those crests. Okay, so the actual quantitative practice for the Doppler effect, of course, I just did a Bombardier Q400 because why not? And so the idea is the plane is taking off towards you with a known speed, making a certain sound, and I want to figure out what the frequency and wavelength that I receive from the plane when it's approaching me and when it's past me. So I have these two equations that I really want to use here, right? I have that the wavelength is dependent on the speed of sound, right, which I'm going to use for V. The speed of the source, so I'm going to use U for the speed of the source. And the reason for that is just so I'm not confusing with U's and V's. So V is always the speed of sound in these equations. And so the frequency of the source, the velocity of the source, and the speed of sound is used to determine the wavelength. And that has this plus or minus inside the equation. Again, super important that we figure out some good intuition about when to use the plus or minus in this equation. In terms of the wavelength, the intuition would be that as the plane is moving, if you're in front of the plane and therefore the plane is moving towards you, the wavelength would be smaller than if the plane was stationary. So the analogy I did in the video was like, I'm walking along the conveyor belt, and so me and the conveyor belt are moving in the same direction, and therefore the spacing between the pies is smaller, whereas if I'm walking in the opposite direction from the conveyor belt, the spacing between the pies would be larger. So in this case, right, when the plane is moving towards me, I want to use the negative sign here because my intuition is that the wavelength will be shorter. Likewise, in terms of frequency gets a little bit more complicated because I have a moving source and potentially a moving receiver. In this case, the receiver is stationary, so I don't have to worry about that. But in general, right, I might have a frequency or a speed of the source and a speed of the receiver here. So here's one thing I do want to say to be extra careful about. I cannot do any kind of fun shifts in reference frame or anything like that. So if the receiver and the source are both moving, I cannot try to reimagine the problem from a different reference frame where one or the other is stationary. If I try to do that, I will get the wrong answer. And the reason for that is I do have a fixed reference frame in the form of the medium. So in this case, the medium is air. The wave is traveling through the air. So that means there actually is a preferred reference frame, like unlike in relativity or unlike in even just like basic mechanics, where I could solve the same problem from the point of view of someone sitting on the ground versus someone sitting on a train. In this case, if I try to do anything in terms of reference frames, because the air is not moving, then I'm going to get the wrong answer. So I don't want to shift to a reference frame where I'm moving in pace with the source or moving at pace with the receiver, because I do have the potential to get the wrong answer. Okay, so there are actually, right, three kinds of solutions to the wave equation. We've kind of been sort of talking about the first two. Pulses, right, are just shapes that I can make on the string. I can make a wide variety of them. One subset would be like harmonic waves, so something that looks like a sine wave times k x minus vt. So that would be something that if I took a snapshot would look like a sine wave, and if I let the timer run, the sine wave would start moving to the right. So both of these are really visible on that PhET simulation that we looked at the beginning of this unit. The third type is potentially pretty interesting, which is if I add up a bunch of harmonic waves that are all just the right frequency, I can arrive at this kind of standing wave solution. And so the standing wave, I've now separated out my sine and cosine function. I've separated out my function of x and my function of t so that now they're being multiplied. So what that means is instead of my wave traveling left or right, my wave is just being multiplied by different amplitudes as a function of time. So as time goes by, the shape of my wave is being scaled by a number rather than the crest moving left or right. So these are called standing waves. Basically, this is how we arrive at any kind of musical instrument. So in principle, like if I want to make waves on a string, right, then if I'm fixing both ends of the string, so I hold them both in place, those points can't move. And that means I can only have certain wavelengths of standing waves to be allowed solutions on my string. So the most basic is what we call the fundamental frequency, and that is really half of a sine wave that exists on the string. So if this is half of a sine wave, then that's a sine wave with a wavelength of twice the length of the string. So in this fundamental, the wavelength is going to be twice the length of the string. The speed of waves on the string is still determined by the medium. So in the case of a string, like tension over mass density. And that means I can find the frequency by looking at the velocity and at the wavelength. So these are called harmonics, and they get these numbered identities because if I double that frequency, then I cut the wavelength in half, and that also fits on my string, right? That meets my two boundary conditions. It's fixed on both ends. And I also get to arrive at this kind of midpoint on the string that also doesn't move. So if you have like a slinky or something at home and a friend, you can make these, right? You can kind of stretch out a slinky between the two of you and start vibrating one end of the slinky, and you can actually find some of these harmonics. So like the slowest vibration will give you this kind of really resonant case with a single point in the middle of the string that oscillates a lot. And if you speed up, you can arrive at harmonics, so second or third harmonic, where basically you're getting multiples of the frequency and you're finding wavelengths, right, such that a whole half number of wavelengths fit exactly on the string. So for the practice problem here, right, we had to find the length of the string, the fundamental frequency and wavelength. Because we know the third harmonic, right, we know that the shape of the wave on the string captured in a snapshot would look something like this. We know the expression for the wavelength, right, would be 2/3 the length of the string. So one wavelength would be this crest and the trough, so that represents 2/3 of the length. And I can relate the frequency, right, in terms of the wavelength and the velocity. If I want to find the fundamental frequency, there's a few ways I can do that. I can straight up cut the third harmonic wavelength by a factor of 3. I can draw the new shape of the wave and identify that I'm going to have the same velocity, but now my wavelength is going to be twice the length of the string. Either way, a few different ways to do it. And the last part sounds really wacky, like, oh, what's the distance to the first anthinode or the fifth harmonic? It's just about drawing out the shape of the wave, really, to get the answer. So the fifth harmonic would be the one where now I have 4 points, 4 nodes, we call them, points where the string does not move, right? So that picture would look like this. And the first antinode is the first point on the string that moves a lot. So the first point from the left end of the string that has a large amplitude of oscillation. And if I just draw the picture, I can identify that's going to be 1/10 of the length of the string. So that's kind of all we're doing for this week. Getting into next week, we'll be looking at other kinds of standing waves, right? So standing waves where I have notes basically made with air. And so what's interesting about these is I can have another kind of boundary condition called an open end. So for instance, if you blow on a bottle, you make a wave like this, where you have a point where the wave is oscillating a lot up at the top of the bottle, and at the bottom of the bottle, right, there's nowhere for the air to go. So that is the point where we consider like a fixed end, like a node. So for the bottle, we can have solutions that look like one fixed end on one end and a free end on the other. So our fundamental actually is a quarter of a wavelength from one node to one antinode. So if I were to keep drawing this, it would be another, right, 3/4 of that wave. I'd have to keep going. So that's kind of interesting because I actually only end up with odd harmonics in this case. If I double the frequency, I cut the wavelength in half, which means I would try to arrive at a solution that looks like this. But this violates my boundary conditions because it doesn't have a free end on the right there. So this would be a node if I doubled the frequency and cut the wavelength in half. So that's not allowed. So the next allowable situation is actually the third harmonic, where I meet both boundary conditions of the fixed end on one end and the free end on the other. Likewise, no fourth harmonic, but I do have a fifth. And so for this one open, one closed end tube, I have only the odd harmonics. And it's just about matching those boundary conditions. So we'll kick off the next unit with that. We'll also get into E&M waves next week and interference. So interference is this special case of what happens when I use superposition to add up 2 waves that are the same frequency. So in some cases, that means the crests and the crests are going to line up and make a bigger wave. In some cases, the crests will line up with troughs to make a smaller wave. And so that we can start expressing in terms of what we call phase difference and then path difference, in terms of if one of the 2 waves has had to travel farther, what does that mean for the interference? All right, so that's the end of the kind of recap of the problems in the unit. Stick around if you've got questions. We can talk more about this stuff. Otherwise, thanks for coming. Or if you're watching the video, yeah, glad you found it.